Hi, this is Donald Winter, and my project is over clean water. So we have some assumptions and conditions with this. We're going to assume that it is pulsé and laminar, which means that there's no turbulence, and the velocity is moving down the tube. It's incompressible. There's no acceleration in the tube. It's a steady flow. The pressure gradient is only in respect to x. So basically, the particles are moving straight down the tube. There's going to be no translation up and down. And that the walls are non-slip. So basically, we just don't want anything that's going to cause this to be turbulent. Those are our assumptions. Okay, this is our given formula that we had, and we took that formula and we integrated it and applied boundaries, and our boundaries is going to be 0 because the walls are going to be 0 because there's no slippage. There's no slippage on the tube. And once you integrate, you're going to get this formula. So basically with this formula, you can find the velocity profile, and you can find for any given input or output what the pressure needs to be to get that. And that's actually what we did in our MATLAB assignment. So let's go to that. Let's see, here is our script. And basically everything's outlined of what we did, but I'll walk you through it. So here's our assumptions, our boundaries. The walls are non-slip. Basically, we don't want anything that's going to make turbulence in our pipe. Here's our inputs. There are outputs. So this is where we called on our data. This data was actually the individual particles inside a tube of water or whatever you want to make it. From this data, we pulled our x positions and our y positions. So basically each particle is going to be assigned to its own y, so its own height in the tube, and the x's are all going to be the same because we want them all down the same spot in the tube or pipe. That's why we have these zeros here. Our pipe dimensions, here they are. This is what we did for the top of the pipe, the bottom of the pipe, the outlet, inlet. It's pretty self-explanatory. So our position in the pipe, we had to move it upward because we had it parameterized to the bottom of the tube, but it needs to start in the middle of the tube because that's where your velocity is going to be the most. We created a drop-down menu, so there's multiple liquids that you can use with our current values. You have fresh water, ethanol, methanol. So we had to take the viscosities of these because to make this non-turbulent, we had to find something called the Reynolds number, and the Reynolds number uses viscosity to, let's see, where is it? Okay, here's our Reynolds number. So it basically uses viscosity to get the Reynolds number through this equation right here. See, it's divided by the viscosity. And then we took the mean of those strictly because we want the velocity or viscosity and the Reynolds number for all of the particles together to see if it's turbulent or not. So back up to here. We had to take the densities also to use to get the Reynolds number. So if the Reynolds number is greater the Reynolds number is going to be greater than, if it's less than this number, then it's going to be laminar. But if the Reynolds number is in between these two numbers, it's going to be transit. And if it's greater than this number, it's going to be turbulent and the whole thing's going to blow up. It's not going to work because our assumption is that it is laminar. So the user is going to input the pressure outlet that they desire. So whatever outlet you want, a sink, whatever you need, we can give you the inlet pressure that is needed to create whatever outlet pressure you are asking for. We're going to plot a cross section of it so you can see the vector field and the flow profile. This is actually where we use that equation. This equation is going to give us this cross section, the vector field. Well, then we polyfitted that to get our pressure gradient of it, and then plotted that information for you. So you can see at any length of the tube basically what the vector field is going to be and what the flow profile is going to look like. So why don't we run this? And it should output some mass flow rates and stuff like that for us. So let's run section. Let's just run it. Okay, so basically it pops up this drop-down menu. So you pick whichever one you want, whatever's going through the tube that you would like. Ours is going to be fresh water for the first time. Let's do 5,000 pascals. So here is our flow profile. So at any given point down the pipe, if you picked a particle or picked a section of the pipe and took the cross section of it, this is what it's going to look like. And then here's our velocity vector field. So this is that equation that we have. This equation at any given point will give you this. Length of the pipe, pipe height. So right now we're using a very small pipe. As you can see, it's a very small pipe. But this could be, you can input any length of pipe that you would want. Only thing that would change here is you'd have to change very minuscule amount of information. Your data coming in would have to be different, and you'd have to change. There's one section in here where we change millimeters right here. Millimeters to meters. No, millimeters to nanometers. And that's where you'd have to change your information given this formula. Okay, so with that we got the mass flow rate, just in case if you wanted to know how much the mass flow rate was for going in the pipe. The pressure change required in order to achieve the 5,000 pascals at the outlet of that number. So basically at any given inlet, with this information you need at your outlet. So this is the 5,000 is your pressure that you put in as your outlet, and this is the pressure needed at your inlet to get the specific outlet pressure. Your flow rate in nanometers, pressure at your inlet is 100. And then your Reynolds number. So basically, this Reynolds number is showing that it is laminar flow. If this was turbulent, none of this other stuff would pop up right. It wouldn't work. So we know, since we have a small Reynolds number, that it is laminar flow. So the water is flowing down the tube with no turbulence. So let's run it again. See what else. Let's go methanol. Let's do 30,000. Here's your flow profile again. Vector field, all your particles. And then this is our outputs. once again, you have your mass flow rate, the pressure change required in order to achieve your 30 pascals at your outlet is right there. Your flow rate is right here, and your Reynolds number is 0.4. So it is laminar once again. Let's see, let's run it a third time. Let's go. Nothing again. Let's do 10. Run it. Flow profile. Vector field. And your Reynolds number. So, with this information, guys, you can basically take any length of pipe that you would like and any outlet pressure you would like and figure out how much the inlet pressure needs to be to get that specific outlet pressure. So that's what we did for our project. Thank you.